Moving on to question 3 now, we have a question here that's looking at product moment, correlation coefficient and regression and the residual sum of squares. So quite a big question overall, there's a few different parts. So what I'm going to do is, because I don't have enough room down here, I'm going to write down in the margins here. So hopefully it's clear what I'm writing. I'm going to do it in yellow so it's a bit clearer. So part A, we have to work out the product moment correlation coefficient between L and W. So it's nothing interesting, it's just looking at rainfall and the yield of leaks, so incredibly boring. But for this question here, we have to use the formula book, okay? So this formula is given to you, and it's just given as R is equal, so I've changed the variables obviously to match for this question, so it'll be WL divided by the square root of SWW SLL, okay? Now, in this case, we've got SWL, that's that, we've got SWW, that's that, but we don't have SLL, so we need SLL. So how do we get that? Again, this is in your formula book, so it's beautiful. You don't even have to memorize any of these formulas. We've just got to work it out. So the formula is given in the formula book as sigma L squared minus sigma LL squared divided by N. And if you read the question, it's the sample here is 10 years, so N is 10. So if I plug everything in here now, well, my sigma L squared, that's 26.2326 minus 16.06 squared divided by 10. Okay, put all that in on your calculator, and what you'll get is 0.44024. Okay, so we've got everything we need now. All we've got to do is use this formula. So SWL, that's 42.786 divided by the square root. So SWW, that's this one here, 9,936.9 times 0.44024. Put all that in on your calculator again, and what you'll get is that R is equal to 647. Okay, so 0.647. Part B tells us that Dora decides to code the data first using these variables here, s equal to w minus 6, and then t is equal to l minus 20. And it just asks us to write in the value of the product moment correlation coefficient between s and t. Now it's only 1 mark, so that should kind of jump out at you that nothing major needs to be done here. And the reason nothing major has to be done is because the correlation coefficient doesn't actually change because of the fact that she's coding. Okay, so r is just simply 0.647 again. And just make it clear that coding will not change the PMCC. Okay, so just 1 mark, it doesn't actually change the PMCC. So let's just clear all that so we've got a bit more room. Part C asks us to find the equation of the regression line of L on W in the form L equals A plus BW. So let's have a go at doing that. So what I've got here is my coded variables, so that's s equals to b minus 6 and t equals l minus 20, and then she calculates it to be this, t is equal to 0.00431s minus 18.87. So let's put all that together now. So t, l minus 20, so l minus 20 is equal to 0.00431 s, where I can substitute s in, and then I can carry on with this. So I've kind of run over a little bit, so this is minus 18.87 at the end. So all I've got to do now is simplify, so just do it down here. Expand this bracket, so you get 0.00431 W, and then this bit here, I've multiplied the 0.00431 with the minus 6, and then perform this with the subtraction here as well of minus 18.87. So doing all that, what you'll get is minus 18.89586. Okay, and then finally all we've got to do to get this in terms of L, so it's L equals A plus BW, we just got to add 20. So therefore L is equal to 0.00431 W, and then if you add this gives you plus 1.10414, and it wants it to three significant figures, A and B. So if we just quickly rewrite that, L will be equal to 0.00431, so that bit's fine. And then this bit here, so three significant figures will be 1.10. Okay, so that's part C done. We've got the values of A and B to three significant figures. Part D just asks us to use this equation then to estimate the yield of leaks when W is 100 centimeters. So really easy, 1 mark, all we've got to do is substitute W equals 100. So part D, W equals 100, sub that in, so L is equal to 0.00431 times 100 plus 1.10. Plug all this in, and what you'll get is 1.54. Okay, and that's the yield of leaks, the estimate of the yield of leaks. Okay, part E, so we're kind of flying through this now. We have to work out the residual sum of squares. So this is better known as the RSS. And again, lucky, this is in the formula book, so we don't have to memorize anything. So the formula for this, so this is what it's given as in the formula book. So it's S, Y, Y minus SXY squared all over SXX. Okay, now obviously this is slightly different to ours because these little variables here are WL, WW, and then it would be LL for the other one, right? But in the case of it in the formula book, it's written as YY, XY, and XX. So you just got to be careful how you decipher this. So the biggest thing is, how do we determine which one's the SYY? Well, look how they've got SXY. Look how they give you in the question, it's SWL. So this bit here minus SWL, so that'd be minus your 42.786 all squared. Now notice, the Y is the second variable. In our case, the second variable is the L. So it's going to be for us S, L, L. And then the other one, it will just be S, Y, S, W, W, sorry. So S, W, W. So plug those values in as well. S, L, L, we know that was, if I just quickly find it, so that was 0.44024 minus 42.786 all squared all over SWW, which was it's given to us 9,936.9. Plug all this on your calculator now, and what you'll get is 0.2560. And there we have it. So that's the RSS, and it doesn't have to be given to any degree of accuracy, so that would be sufficient there in that case. Part E gives us the graph of the residuals for each value of L, and it just asks a couple of little things. Part I here asks us to state whether this graph suggests that the use of a linear regression model is suitable for these data. So F part 1, well, what we can say is that the points appear to be randomly scattered, right? If you look, there doesn't seem to be, you know, an apparent trend to this model. So what we'd say here is that the points appear to be randomly scattered. And because they're randomly scattered above and below 0, that gives us no reason to doubt the suitability of a linear model. So therefore, no reason to doubt the suitability of a linear model in this case. Okay, so that's just 1 mark, but it's just, you know, it's the last part of the question is, you know, it's just a little bit of finer detail to the question. Okay, so because they're randomly scattered above and below 0, we've got no reason to doubt it. And then the second part, part 2, it says, other than collecting more data, suggest how to improve the fit of the model in part C to the data. So if you look at this graph that they've given us here, hopefully there's one thing that's jumping out at you, and it would be this point here. Okay, this appears to be an outlier, so outlier. So because of this is going to skew the data ever so slightly. Now, what we could say is that if we remove the outlier, so we remove outlier, so remove that outlier, and then recalculate the regression line, oops, I've accidentally thinned the font. So we recalculate the regression line. This could improve. This may improve the model. So there we go. So that's the very final part for that question, and that's question 3 fully complete.